welcome back to this online short course by Red Door Analytics, Survival Analysis, and Introduction to Concepts, Methods, and Software. In this section of the course, we'll be talking about the proportional hazards assumption and how to assess this. So far, we haven't discussed the proportional hazards assumption more than saying that the Cox model is called the Cox proportional hazards model because it makes this assumption, but what this assumption is, we haven't covered yet. So this proportional hazards, or pH, as it may be written in the slides, assumption is a fundamental assumption to consider in survival analysis methods when modeling. So what is this assumption? Well, when we assume proportional hazards, we assume that the effects of all covariates in our model, exposure or confounders, are constant over the time scale. So what I mean by this is that any hazard ratios are constant across the time scale. So when we assume proportional hazards, we present a hazard ratio which represents some sort of average across the whole of the time scale. This assumption is often violated, especially when we have long follow-up times. And we'll discuss how to address or assess the proportional hazards assumption in this section of the course. So the opposite of assuming proportional hazards is assuming non-proportional hazards or allowing for non-proportional hazards. So when we relax the proportional hazards assumption, we allow for the effect of at least one covariate in our model to change over time, which is the same as including interaction in our models between the covariate of interest and time. And this basically means that we have, then we will get a hazard ratio out of our model that varies across our timescale. So note that under proportional hazards, hazard rates can still vary across the timescale. And this is model dependent. So if you remember back to our section on parametric survival regression, we saw that in the Weibull model, the underlying hazard rates were allowed to change over time. They weren't constant across the timescale, but the hazard ratios were constant across the timescale. Hazard ratios are always constant under proportional hazards. This is what it basically, the proportional hazards assumption means. But when we relax the proportional hazards assumption, we can allow for hazard rates vary across the timescale, always. They will no longer be constant. But the hazard ratio for at least one covariate can vary across the timescale, and this often can be the exposure of interest, but it doesn't have to be. So to illustrate this, I have a graph here which shows you on the left-hand side proportional hazards versus non-proportional hazards. And we present this on the log scale. The Y scale is the hazard rate, but it's on the log scale so that you can see clearly the differences, because we see a constant difference in the hazard rate on the log scale. So if you look at the left-hand side of the graph, we have a hazard rate per person year across here, some time scale, which is time since diagnosis. And this is within our example of hormonal therapy and no hormonal therapy, where I've fitted some piecewise exponential model where we allow the rate to change across the time scale, but in a stepwise fashion. So we have a constant rate within windows of time. So you can see that on the log scale, the difference in this time period between the hormonal therapy and the non-hormonal therapy is exactly the same as in this period, where we allow the underlying rates to change, but the difference is the same. And then we can see that across the different time periods, again, they both go down by the same amount. So the difference between these two lines is the same. And again, the difference is constant across the whole of the timescale, despite the fact that we allow the rates to vary across the timescale. Now, under non-proportional hazards, we may see something like this, where we basically see that the differences are no longer constant. So here we can see we have a much larger difference between the no therapy and the hormonal therapy group than here, where we have a smaller difference. And again, if we look at the last period, for example, they're almost the same. So you should be able to see that if we take a ratio of these two rates at different time points, that we get different values. The ratio will be different. And on this time scale, on proportional hazards, we get that the ratios are the same. So the hazard ratio is constant across the time scale. So if we were then to plot the hazard ratio from these two plots, and now we have that the blue line represents the proportional hazards estimates in the previous slide, and the orange line represents the non-proportional hazards, we see that from the proportional hazards, we get a constant hazard ratio of around 0.7, which is consistent with what we found from our previous models, which assumed proportional hazards in the previous sections of the course. But then when we allow for non-proportional hazards, as we did in the previous slide here, we allow for non-proportional hazards, we then estimate the hazard ratio at each of these time points and plot this. This is what we do here. We can see that this hazard ratio jumps around, so it's allowed to vary across the time scale. This is essentially what we mean when we say, are we willing to make the proportional hazards assumption or not? Do we believe that the hazard ratio is constant across time for all of our covariates, or do we believe that it varies in some fashion? Another example here we have from smooth models. So these are are estimated from flexible parametric survival models. The code is in the do file if you're interested in how to do this. But here you can see on the left-hand side of the graph, we have hazard rate across our time since diagnosis, where the blue lines represent a proportional hazards model and the orange lines represent a non-proportional hazards model. And then we have solid lines representing the hormonal therapy and dashed lines for the no therapy patients. So when we look on the hazard scale, you can see that they look quite similar actually on this scale. But then if we calculate the hazard ratio across time since diagnosis, you can see this assumption very clearly, that when we make the proportional hazards assumption, we have a hazard ratio that's constant across the time scale. And then under non-proportional hazards, we see that we have hazard ratio that is steadily increasing, goes over the 0.7 estimate, and then it starts to decrease until it becomes almost the same value as from the proportional hazards model. So I think it's important to just talk about a little bit about terminology in terms of proportional hazards, because there are a lot of ways to say this and a little bit of confusion surrounding some terminology. So the following terminology all refer to non-proportional hazards. If you say that you include a time-dependent effect in your model, this basically means that your effect, or you can think of it as being your betas that are estimated from the model, can vary across time. You include an interaction between these variables, the covariates, and time. So this is allowing the effect of a coefficient to change over time, so your hazard ratio. But this is not the same as a time-dependent covariate. Think about this. This is time-dependent effect, not a time-dependent covariate, where the value of your covariate changes over time. That is a different thing. You can also say, to refer to non-proportional hazards, that you are including an interaction between your covariate and time. You can say that you are relaxing the proportional hazards assumption. And to have non-proportional hazards, model that is assuming non-proportional hazards, it means that you have to have at least one time-dependent effect in your model. You can have more than one. But if you have several covariates in your model and you allow for one hazard ratio to change over time of one covariate, but not for the others, that is still a non-proportional hazards model, but it allows for the effect of that specific covariate to vary across time. So luckily, we can test this assumption, which is very nice. And there are different ways of doing this. There's something called a log-log plot, which can be used for categorical variables. You can look at observed versus predicted survival. There are tests based on Schoenfeld residuals. And you can test for the inclusion of a covariate time interaction in survival analysis regression models. So we'll go through these one by one. So let's start with the log-log plot. So this is a plot of the minus log survival function, and a violation of the proportional hazards assumption exists if the lines that you plot are not parallel. So here we can see an example of this, where on the y-axis we have the minus log of the survival probability, and on the x-axis we have the log time. And what you should look at is, okay, do we think that these lines are parallel or not? So this is a little bit subjective to see. From this plot, what I would say is that they look quite parallel. There's some stuff going on up here, but you can see that there's not so much data here because the dots represent data points. So if we go to our study example, just to remind you what that was, this is looking at German breast cancer patients. We follow them from diagnosis of breast cancer until the time of event, where we are looking at recurrence of breast cancer or death in patients. So we will consider the case where we're interested in including 3 covariates in our model: hormonal therapy status, which is a yes/no variable, hormonal therapy or not; age at breast cancer diagnosis, which is a categorical variable with 3 categories; and grade of cancer, which is an indicator variable for did you have grade 3 cancer or not. So in Stata, we can use a command called stphplot to get the log-log plots to assess the proportional hazards assumption. And we would get something that looks like this. So we have 3 different plots for the different covariates of interest. And here what I've done is I've just put them next to each other. So on the left-hand side, we can see our hormonal therapy status. Actually, this is the same plot as I presented previously. So we can see that it looks like there might be some violations here. It's not always exactly the same distance between the 2 lines. For age at diagnosis, this looks a little bit more severe, that they are not the same distance between or parallel lines. And then for grade of cancer, we also see that it looks like there's a gradual joining of the 2 lines towards the end of the log time since diagnosis. And if you want to plot these yourself in Stata, here's the commands that you can use. These are 3 separate plots that you would create using stphplot, and then at the end I combine these to get the graph as I have in the previous plot. And basically you would use stphplot, and then you use the by option to give the variable that you would like to see the plots by. And then there's some options for the graph here. Again, this is not exactly the same code that I've used to produce the graph in the previous slide, but they are available in the do files as part of the course material if you wish to replicate the figures in the slides exactly. So some things about this log-log plot, I would say that the interpretation of the plot is quite subjective. I think some people may say that, yes, definitely these are parallel. Some people may overinterpret a wiggle a little bit more than others, so that can be quite problematic. But if the lines are not parallel to each other, then the proportional hazards may be violated. So that's what it means. So what I've concluded here from those slides is that there may be a bigger difference for grade than the other 2 plots, because we saw that this gradual joining of the 2 lines, which may indicate a potential problem with the proportional hazard assumption for grade. Now, the second option we could use when we want to assess the proportional hazards assumption is to plot the observed versus the predicted survival. So what this is a plot of the Kaplan-Meier survival versus predictions from a proportional hazards Cox model. So we get the observed values are from the Kaplan-Meier and the predicted are from a proportional hazards Cox model. So the less likely we have a violation of the proportional hazards assumption, then we would have the values closer to each other. So we would assume that observed and predicted would be really close if the proportional hazards assumption was a reasonable assumption. So here on this plot, you can see an example of what this would look like. We have the survival probability on the y-axis and the time since breast cancer diagnosis here on the x-axis. And this is the example for hormonal therapy in our study example. We can see that the blue lines represent the predicted values from the Cox model for the hormonal therapy. And behind them, we can see there's some grey dots or grey line, which represents the observed values estimated from the Kaplan-Meier curve for the hormonal therapy. And then for the no therapy group, the orange dots here, we can see there's also a grey shadow behind, which represents the observed values. So what we want to see is that these basically overlay each other, that we don't really see any grey lines would be great. And then we could say that the proportional hazards assumption seems reasonable. And actually, we don't see that much of a difference here would be my conclusion from these. So how we can do this in Stata is we can use the SDCox-KM command to get these plots of predicted survival versus the observed survival in order to assess the proportional hazards assumption. And here I show you 3 plots again for the 3 covariates we're interested in. Here we have the hormonal therapy status, which I just presented to you. And then we can see what it looks like for the different age groups. And then you can see quite clearly here, there's a little bit of deviation in the grey observed values for the oldest age group. But remember that there's maybe fewer data there. And then we also see maybe a little bit of deviation from the 50 to 64-year-old group here. So there may be potentially a problem with the proportional hazards assumption for age at diagnosis from this plot. And then the grade of cancer here is presented on the right, and we can see again that the grey values are the observed values, and the blue and the orange are those predicted from the model, assuming proportional hazards. And we can see that here we have some sort of deviation from the observed values deviate a little bit from the predicted values. It looks like this predicted survival from the Cox model maybe isn't capturing what's actually happening in the observed data for the grade of cancer, indicating again we may have some issues with grade of cancer when it comes to the proportional hazards assumption. If you want to predict these values yourself, you can use the commands here where we predict the curves separately using the SDCox-KM command. And then we combine them using this graph combine at the bottom to get the graphs side by side. And basically what you have to do is use this by option to specify which variable you would like to look at within each. So you can see the top one we use by hormone, the second one is by age cat, and then by grade 3. So what is the conclusion from looking at these graphs? Well, the hormonal therapy status plots, the observed and predicted are quite similar. There's some larger difference in the observed and predicted values for age at diagnosis of grade and grade of cancer. So this would indicate that there are potential violations of the proportional hazards assumption for age at diagnosis and grade of cancer. So the third thing we can do is we can look at something called the Schoenfeld residuals. And so what we want to do is look at plotting these residuals. So these are just a type of residual that we plot, and then we have some smooth line on these plots, as you can see here, that we want to see that this is flat. So if this line is flat, then we have evidence that the proportional hazards assumption may be a good a good idea. If it's not flat, then we may have a violation of the proportional hazards assumption. So here I show you for a categorical variable, and we see we've got two separated lines of residuals here representing the category. So it's maybe less interesting to look at these in a continuous variable. And we see there's the smooth line, which looks, I would say, quite flat. If we want to look at a continuous variable, we can see the residuals a little bit like more scattered just because we have a continuous variable rather than a categorical variable. And here, this is for age. We can see that there looks like there may be a little bit of deviation from that flat line. It looks like it starts a bit lower and increases and then flattens out. So if we want to do this in Stata, we can do this using the estat-ph command to get the Schoenfeld residuals out and to plot these to assess the proportional hazards assumption. So this is what I do here. I'm showing you 4 different panels here. This panel on the top left represents the hormonal therapy status variable. We have age diagnosis for 2 of the different groups here. And then we have grade of cancer in the bottom right here. And if we just focus on those lines, those blue lines for each of these, I think that the one that sticks out the most, at least, is grade of cancer, that looks like it starts a bit higher and then decreases and then flattens out, and maybe after 4 years. There may be a little bit of an increase and then flattening out for both of the age categories here, but I would say that hormonal therapy, the line looks quite flat, and so that would say that probably for hormonal therapy, proportional hazards is probably a reasonable assumption. And then for grade of cancer, it seems like proportional hazards is not a good assumption. We should probably relax that assumption. If you want to plot these yourself in Stata, here's some code. Again, the same thing, I plot these separately and then combine them at the bottom. And you can see here that we've got different plots for the hormonal therapy, then for the 2 age categories, and then for grade at the bottom. So what do we conclude from these lines? We say that the smooth lines are quite flat for hormonal therapy, but less so for grade of cancer and possibly age at diagnosis. So these indicate that there may be some deviations from the proportional hazards assumption for grade, and possibly age at diagnosis. So the other part of the Schoenfeld residuals is you can plot them, as we said, and look at that smooth line, but we can also perform a statistical test, which I think is really nice. And basically this tests whether the slope of the smooth Schoenfeld residuals line that we saw is statistically different from 0. So this removes some of the subjectivity involved in looking at those graphs and deciding, okay, is this flat or not? So when this is statistically significant, it would suggest that there is an evidence of a violation of the proportional hazards assumption. So what we can do is we can fit a SD-Cox model here with hormonal therapy included in it. We can then use this estat-ph test command and use the detail option to perform this test. And what we would see in this model that only has hormonal therapy, we would see this output which says test of proportional hazards assumption. And the thing that we're most interested in is these p-values at the end. So these are the tests for, basically the residual line statistically different from 0. So our p-value is greater than 0.05. So from this, we would conclude that there is no evidence of a violation of the proportional hazards assumption, and that proportional hazards seems like a reasonable assumption. Okay, so as I said, we can use the SDS-pH test command to perform a proportional hazards test after fitting our Cox model. What we will do first is fit our Cox model, and here we're going to use the 3 covariates that we're interested in, that is hormonal therapy, the age category at diagnosis, and grade of our cancer. And then we use the estat-pH test command, and we use the detail option to get some information out about the separate variables. And this is the output that we get. We can see now that we have hormonal therapy, age category, and grade included in here. We also have a global test, so we have probability compared to a chi-square distribution, giving us a p-value for each of these. So if we look at the hormonal therapy, we see that the p-value is greater than 0.05, which would indicate that proportional hazards seems like a reasonable assumption for this variable. When it comes to age category, we see that we have a value that's less than 0.05 and greater than 0.05, which leaves us in a bit of a pickle, because we don't want to treat the different age categories separately. We want to deal with them together. So we can't separate out the different ages, or we don't want to in this model. So what we would conclude from this is that we may have a problem with the proportional hazards assumption from the age category, but it may be limited to one of the age categories. But it's more clear for the grade category, where we see we have a value of 0.009, which would indicate that there is a violation of the proportional hazards assumption here for this variable. And this is most likely what's driving behind the global test, which also indicates that this should not be a proportional hazards model. We should be including non-proportional hazards somewhere in our model. So we see that there's evidence that the proportional hazards assumption is violated for grade of cancer, and this is in alignment with the conclusions from our other assessment methods. So another way to assess the proportional hazards assumption is to perform a statistical test, such as a Walder likelihood ratio test, for the inclusion of an interaction between the timescale and the variable. So if we go to our study example and looking at Stata, we can use the LR-test command to perform a likelihood ratio test, comparing the models with and without an interaction term. So we will start by using the streg command. Here I've got an option QUI, which stands for quietly. It just means that there would be no output in Stata from this. It would run this model in the background, but not give you the output that we normally would see. So I fit the model here, and this is an streg, an exponential. If you look at the distribution here, we have distexp. So we fit an exponential distribution model here, but we include this follow-up variable, FU. So what we're actually fitting is a piecewise exponential model. So we allow the rates to change across the time scale in these three different time categories, if you remember before, that go from 0 to 2 years, 2 to 5 years, and 5 to 8 years. And then we also adjust for hormonal therapy, grade, and age category. And what we do is we say to Stata, please save this model in the background somewhere using this estimates or est store, and save it under this, we're going to call it model 1. So Stata is going to say, okay, we know that this model that you've just fitted, this piecewise exponential model, adjusting for these variables, we're going to save it in this thing called model 1. And then we do exactly the same thing, but what we're going to do now is we're going to include an interaction between the follow-up time, so our time scale, which is represented by the FU variable here, and the variable grade. As you can see here, it's denoted by this double hash. So the only difference between the first model we fit and this model here is that we have include an interaction term using this hash formulation in Stata. And then we do the same thing and tell Stata to save this model called model 2. And then we use this LR-test command to say, okay, please perform a likelihood ratio test comparing model 1 to model 2. And we will get this output here, where we're interested in this probability, this p-value, which is 0.0122. So this says that basically we should reject the null hypothesis that the models are the same, indicating that the model that's more complicated, the model with the interaction included in the model, is a superior model. Because this is less than 0.05, which means that we should include this interaction in the model, meaning that we should be allowing for non-proportional hazards of grade here. So we see that there is evidence that the proportional hazards assumption is violated for grade of cancer, and this is in alignment with conclusions from other assessments. So I've given you lots of methods to use to test the non-proportional hazards assumption, but which one should you be using? So I thought it's a good idea to just talk about some of the strengths and limitations of each method. So if we start by thinking about the log-log plot, the survival observed versus prediction plot, and the Schoenfeld residual plots, the first three options that we discussed, then I would say that these are quite subjective, or at least like the conclusions you draw from them are quite subjective. The fact that you have to look at the plot and make a decision based on your personal opinion. I mean, of course, if there's a really clear evidence of non-proportional hazards, hopefully the majority of people would draw the same conclusion. But there can be some grey areas where you may have a different opinion to someone else, and that makes it quite subjective, which I think is a limitation. Another limitation is that you have to perform these separately for all covariates. As you saw, I predicted the values needed for each of the plots, or plotted them all separately, and then looked at the covariates one by one. So you have to do this for all of the covariates. If we then take the Schoenfeld residual statistical test, I think this is a bit better. You can perform a global test, which is really nice. And you can also see the separate p-values for each variable. So it's nice to have that combination of the overall and the separate values. The one problem with the Schoenfeld residual test is that it may miss U-shaped relationships. So if you remember that we plotted these and we had the line that we saw across the residuals, if this was a U-shaped relationship, it may not be able to see this. So then you would want to also look at the graph actually. And then the test for inclusion of the interaction, well, you have to perform this for all covariates. In the previous slide, I only performed this for the grade variable because at this point we already sort of knew that this one might not be a reasonable covariate to have proportional hazards assumption for. So you do have to perform tests for all of the covariates in the model. So what do we do when the proportional hazards assumption is violated? As we saw in our previous examples looking throughout, we saw that grade is violating the proportional hazards assumption. We also saw that age may also violate the proportional hazards assumption. So what do we do about that? Well, what we would do is include interactions between our time variable and the variable where the violation has occurred. So as you saw in the previous slide where I included this interaction in our piecewise exponential model, you would just fit that model and that would be your model that you would use for your interpretation. Another thing that you could do is you could run analyses in separate subgroups for this non-proportional hazards variable. So you would make no assumption about the relationship between those two groups. So if we're looking at the grade variables, we would get hazard ratios for the hormonal therapy versus no hormonal therapy in those that had a grade 3 cancer and those that did not. So you would get very different hazard ratios, and that would also account for the non-proportional hazards assumption. So in this way, you essentially allow for interactions between every variable in your model and the variable that you have the violation of the proportional hazards assumption. Another option would be to fit a stratified Cox model. So this basically allows for separate baseline hazards for levels of the non-proportional hazards variable. So if we take the grade variable as our example, what it does in the background is that it allows for the separate baseline functions. So although in the Cox model we don't directly estimate the baseline hazard function, you can imagine that it does allow these to be completely different. So the shapes don't have to be related to each other at all for the grade not being 3 and the grade being 3 for that specific example. So yeah, since the baseline hazard is not estimated in Cox models, this should only really be used for nuisance variables because you would no longer get any estimate for that variable. So if we were to fit a stratified Cox model for the grade variable, stratifying on grade, we wouldn't get any estimate for grade. We wouldn't know the effect of grade on our event of interest of recurrence of breast cancer or death. We would just know that, okay, we've dealt with the non-proportional hazards. So we've covered a lot on proportional hazards here. We've spoken about how to assess this in different ways. And in the next section, we will be talking about fitting non-proportional hazards models a little bit more in depth. For now, here's some further reading, and I will see you in the next section.